Okay. Ever burn your mouth on the filling of a hot meat pie when the crust is totally fine?
Oh, yeah.
We've all been there, right? But did you know that like that whole experience is like a gateway into the fascinating world of energy?
It is.
That's what we're diving into today. The core of what energy is, how it transforms, and why that even matters. Let's start with the basics. What is energy?
Yeah.
Our sources all pointed to, pretty much a common definition: the ability to do work.
It sounds simple, but it's quite profound when you think about it, right? Like anything that can cause change, whether it's, a ball soaring through the air or a plant converting sunlight into food, all of those things possess energy.
So like that toy car you see going down a ramp, that's energy in action.
Exactly.
Yeah.
Yeah, that car has kinetic energy due to its motion, which comes from the energy that's stored within it being transformed. That's actually a really crucial point here. Energy isn't static, right? It's constantly changing forms. It's like a master of disguise.
That's what's always fascinated me about energy. It never just disappears, it just transforms.
Right.
It's like energy's playing this constant game of hide and seek.
It's more like a magic show, really, if you think about it. But you're right, energy is never truly gone. It just changes form. And to really understand these transformations, we need to define the system we're looking at.
So kind of like putting a frame around a specific process and seeing how energy behaves within those boundaries.
Precisely, yeah. It helps us track how energy moves and changes within that system.
Yeah.
Like taking a before and after snapshot in a way. Yeah, LOL charts, they help to break down complex energy transformations into these like easy to understand diagrams.
Yeah.
It makes it much easier to see how energies can surge within a system.
So instead of getting lost in the vast universe of all energy, we're focusing on like a smaller piece of the puzzle.
Exactly.
Okay, this is where it gets really interesting to me. Can we dive into some specific examples of these transformations?
Absolutely. Let's start with one that's happening all around us all the time. Convection.
Okay, convection. So I'll be honest, my understanding of convection usually stops at heat rises.
Yeah, it's a common simplification, but there's more to it than that. It all comes down to density. When fluids, like liquids or gases, are heated, their molecules become way more energetic and spread out, which makes them less dense.
And because less dense things tend to rise, that warmer fluid floats to the top. What happens to the cooler fluid?
Exactly. And that cooler, denser fluid, it sinks to take its place. This like continuous cycle of rising and sinking, that's what creates a convection current. It's like a natural conveyor belt, for transferring heat.
So it's not just hot air rising. It's this constant flow. That's super fascinating.
Yeah, and incredibly important. Think about something as simple as like boiling a pot of water for pasta, right?
Mm-hmm.
The heat from the stove that warms the water at the bottom, which becomes less dense, and then it rises. That's what creates those currents that we always see in the pot. And without convection, you'd end up with like a scorching hot layer of water at the bottom and then like lukewarm water at the top.
That explains why we stir pasta. We're basically just helping those convection currents do their thing and distribute that heat more evenly.
Precisely. And it's not just cooking. How car engines actually rely on convection for cooling. So the hot coolant, right, after it absorbs all that excess heat from the engine, it becomes less dense and it rises into the radiator. Then that radiator cools the coolant down, making it denser, so it sinks back down to the engine, ready to absorb more heat.
So convection is like quietly working behind the scenes to keep our cars from overheating this whole time.
It is.
I never realized how vital this process actually is. What about those refreshing sea breezes that you get on a hot day at the beach? Is that convection too?
During the day, the land heats up faster than the ocean, right? The warmer air over the land rises, and then the cooler air from the sea rushes in to take its place, which creates that, that sea breeze that we all love. It's the same principle, just on a much larger scale.
Wow, I never realized how much density plays a role in our everyday lives. From a simple pot of water to the weather patterns we experience. It's crazy how these fundamental physics concepts have such an impact.
That's the beauty of physics. But speaking of fundamental concepts, we can't forget about electricity. It's another form of energy that's just completely ingrained in our lives, even though its inner workings might seem a bit mysterious.
Yeah, it does feel kind of like magic sometimes, right? Like you flip a switch and suddenly light.
It really is. So think of electricity as the flow of these charged particles, usually electrons, through a conductor.
So water flowing through a pipe.
That's a great analogy. And just like water needs pressure to flow through a pipe, electricity needs what we call voltage to push those electrons along. And this flow of electrons is what we call electrical current. And it's that current that powers, all of our devices. But, all this talk about electrical energy and how it flows, it kind of reminds me of another key concept that we need to unpack: specific heat capacity.
Oh, right. We can't forget about that burning hot meat pie filling. It was holding on to that heat with a vengeance.
And it all comes down to this concept of specific heat capacity. Like different materials, they have different abilities to store heat, and that's exactly what specific heat capacity measures.
Okay, I'm intrigued. Let's dive into that. All right, specific heat capacity. Back to that meat pie mystery. Why was that filling SO determined to stay scorching hot?
Okay, so different materials have different abilities to store heat.
Okay.
And we measure that with, you guessed it, specific heat capacity.
Makes sense.
So some materials are like thermal sponges, right? They just soak up heat energy and hold on to it for dear life.
So the higher the specific heat capacity, the more heat it can actually hold. Like those, those hand warmers that you click to activate?
Exactly. Think of it this way. Materials with a high specific heat capacity, they have like bigger thermal piggy banks, right? They can take in a ton of heat energy without like drastically changing their temperature. Take water, for instance. Water has a surprisingly high specific heat capacity.
Yeah, that makes sense. It takes a while to boil, but once it's there...
It stays warm.
Yeah.
And that's also why, like, taking a quick dip in the ocean on a hot day doesn't leave you feeling like you're swimming in a boiling cauldron.
Right.
But let's bring it back to your burning hot meat pie filling, right? Filling, because it has a higher specific heat capacity, it absorbed a ton of heat energy from the oven and was very reluctant to let it go. The pastry, though, not so much. Lower specific heat capacity, it heats up quick, but it also cools down much faster.
Mystery solved. So it wasn't just me being, impatient for that first bite, it's physics.
There you go.
But this isn't just about, me burning my mouth on a meat pie. Knowing about specific heat capacity, this has real-world applications.
Absolutely. Think about radiators. They're typically made from materials that have, those high specific heat capacities like cast iron or aluminum. That way they can absorb a ton of that heat energy. And then they can radiate that heat steadily, that nice even heat to warm up your room.
I'm seeing specific heat capacity everywhere now.
Yeah.
From my coffee mug in the morning to my heating system in my house.
It's amazing how these concepts, once you understand them, they just start to reveal themselves all around you.
It really is. We've covered so much ground in this deep dive today.
Right.
From the fundamental definition of energy and how it transforms to exploring those wild convection currents and even the role of specific heat capacity. It's a lot.
It is. And don't forget about those LOL charts. Those are a game changer. When you're trying to visualize and understand energy transformation, like in all sorts of situations, super helpful.
Yeah, those are definitely going on my list of things I wish I had known sooner about. But before we wrap up, any final, mind-blowing thoughts to leave our listeners with?
Well, so we've talked about, how energy transforms, how it's transferred, all of that. But there's this often overlooked force at play in all these examples we've been talking about.
Oh, okay.
Gravity.
Okay.
From that toy car racing down the ramp to those convection currents, even something as simple as picking up a book, lifting a book. Gravity influences how we experience and use energy. It's a fundamental force that shapes, literally shapes our world.
That's such a good point. I never really considered how gravity plays into all of this.
Yeah, it's easy to overlook, but it really is like this invisible hand that's shaping so much of what we see around us, even down to how energy behaves.
Wow. This deep dive has given me a totally new perspective on something that, honestly, I thought I already understood. I'm going to be looking at the world a little differently now after this.
I love that.
Thanks for joining me on this journey into the world of energy. Until next time.